Okay, I don't know. Okay. Oh, I didn't record earlier, but it's okay. Alright. Now, okay. Alright then, let's go. Here's the thing. Now, what does it say here? Now, typically, right? Okay, if you have this opening of sluice gate, you have sort of like a box opening, right? So it's sort of like a rectangular orifice. That means you are discharging. I think in your fluid mechanics you have learned about orifice. Normally is circular, right? But if you have this kind of opening, of course it extends to the width of the channel. Therefore, it's kind of box opening. So it's termed as rectangular orifice. And then now. As long as the height of gate opening A is smaller relative to E naught. Of course, if the gate opening is as large as E naught, where is E naught here? If the gate opening is as large as E naught, then this gate serves no function as to control the flow, right? It will just like freely discharge this there, okay? Now, and then a flow further downstream Y2 does not affect flow under sluice gate. Now, what it says here is, alright, this Y2 does not submerge this. Sometimes, alright, you'll see that this Y2 will come out and drown Y1. So it's actually affecting the flow, alright, out of the sluice gate. Now, the minimum depth area here, which is Y1. If you look at this, right, this is your Y1. This is known as known also as vena contracta. Vena contracta is the location which you have the smallest depth and highest velocity. That it is termed as vena contracta. Alright. Minimum depth area, maximum flow velocity. You know that Q with constant discharge, Q equals to A times V. That means Q is directly proportional to A and V. If A is small, V is large, right? So it works is directly proportional, right? Now, we have to look at this previously. Now, if we want to analyze flow under sluice gate, right, okay, we will be looking at 2 points here, point 1 and point 2. We are looking at, we are using Bernoulli's theorem to analyze it. At the top surface, right, at upstream of sluice gate, pressure is atmospheric pressure, so pressure is 0, as well as here, pressure is 0. Now, you know that by now, right, if, okay, you have sluice gate, okay, Y1, okay, you have flow coming out, right? This velocity, alright, is actually quite high, alright, because you have high initial energy of flow. Now, here's the thing. When this come out, alright, you would notice that the velocity at this point here is actually going downwards, alright, because it's not going horizontally. So the velocity is going downwards, and the velocity is very small because you have a huge upstream storage, right? So the velocity is 0. Therefore, you can assume this as 0 compared to the velocity coming out from the orifice, right? The rectangular orifice or the opening of the sluice gate. Now, therefore, alright, if we are taking, alright, Bernoulli's theorem at 2 points, which is point 0 and 1, the pressure at not or 0, and at location 1, because it's measuring the atmospheric pressure, is 0. This is almost 0, so what you have is y0 equals to y1 plus v1 squared over 2g. Now, I actually rearrange y0, y1 to the other side. I have this equation here. Now, my purpose is to find discharge out of the sluice gate. So, I'm going to have my velocity to be the subject of the equation. So, I have v1 square root, because it's square. So, we square root of 2g y0 minus y1. Now, discharge is the flow area times velocity. Now, our flow area is actually A times B. A is the height of the opening. B is actually the width of the channel. So, you have A times B, velocity. Now, CD would be the coefficient of discharge, because we know that, alright, the discharge that comes out, right, is actually smaller, or the depth is actually smaller than the A. So we have this discharge coefficient, right, to actually correct, okay, since the opening it doesn't have smooth flow, right, okay, it actually have it actually reduces, right, the discharge. So you have coefficient of discharge, right. Now, if you ask me where does this value comes from, for example, 0.596. Now, if you look at papers, people doing experiment, right, and they presented it into a paper, in the form of paper, you probably would see a different value. Is that this actually comes from experimental data. When we talk about experimental data, you have to read through the paper, because the condition of each experiment is different. Alright, so typically, so far, alright, we'll just use this value. Now, here's the thing. The question would either give you coefficient of discharge, or they will ask you to calculate the coefficient of discharge, or they will give you a set of formula where you can calculate all this coefficient of discharge. Take note, alright. Question might give you directly, or you need to determine the coefficient of discharge. Alright, now, what would be the formula? Alright, now, just now we talked about, y1 could be submerged. Alright, now, if y1 is submerged, alright, that means y1 is relatively small, or it's actually not affecting the discharge coming out, then you need to consider y2 instead. Therefore, look at this. Alright, if y0 minus y1 is actually smaller than y2, that means y2 is larger. Right now, you should know where is y2. Y2 is at this location, y1 is this location, and y0 is the depth behind the sluice gate. If y2 is dominant, you have y2 here. Whereas if y0 minus y1, or actually if y2 is small, alright, you have y1 in the equation, which will actually, influence the discharge. So this is the discharge equation, alright, and you need to check the condition of difference of y0 and y1 and compare it with y2. Then you know which equation you want to use. Now, let me tell you this. Chapter 5 on hydraulic structure is kind of straightforward. Okay, normally, it is more to the application of the equation, but it might involve some analysis as well. But of course, you have the design part as well for the steaming basin. Now let's look at this one, activity 5.1 here. You have a sluice gate, alright, which is built in a rectangular channel, the bottom width. Alright, in previous chapter, right, the width of the channel we have used capital B or uppercase B. This is actually the same width. Alright, only that in this chapter we have used the lowercase b, right? The width of the channel is 1.5 meter. Alright, and then the flow and gate characteristics are one knot, which is the depth behind the sluice gate, is 0.35 meter. Alright, and then you have the discharge. The coefficient of discharge 0.61, and the height of the gate opening is 0.12 meter, which of course should be smaller than 0.35 lah. Find discharge under sluice gate if y2 equals to 0.2 meter. Now we know that if you want to find the discharge, we need to find the difference of y0 minus y1 and compare it with y2. What is our y1? So the first thing is we need to find y1. We know that y1 is this depth correction factor times the height of gate opening, which is A. So y1 is sine times A. So you have 0.63 times 0.12. You have y1, the depth. Just downstream of the sluice gate, you have 0.0756 meter. Now, what's the difference of y0 minus y1? 0.35 minus 0.0756, you have 0.2774. If you compare it with y2 is 0.2 meter. Alright, so could I have is Siti Azlin there? Siti, are you there? Siti Azlin. Siti Azlin, can I ask you a question? You are not responding, eh? How about okay, let me ask Nurul Izwaniza. Is Nurul Izwaniza there? Can I ask a question? Nurul? Can you guys hear me, by the way?
Can, Doctor.
Can, eh? Okay, who is answering me just now?
Cuma mic Doktor macam pecah-pecah sikit.
Oh, you ke? Tadi tak cakap. Okay.
Ada yang jelas, ada yang tak jelas.
Alamak, okay. Sekejap I'm going to fix the mic for a second. Okay, how about now? Is it clear? Pun pecah-pecah
Macam sama je.
Kejap. Okay, maybe the fan. Macam mana sekarang, lebih baik?
Lagi baik.
Okay, thank you. Saya rasa kipas ke. Now, boleh saya tanya soalan tak? Who is answering me? Help me. I want to ask you one question. If you compare y0 minus y1 with y2, which one is more dominant? May I know?
Doktor tanya siapa?
You.
Oh, okay. Yang
Why not?
Why not minus y1?
So the equation that you are supposed to use, you need to consider that, right? Agree? Okay, that's good. Okay, thank you. Siapa tadi? Yuslan. Okay, great. Thank you, Yuslan. Okay. Now, so far, okay, that's the trick lah. Is that very direct, this question, similar to activity 5.2. I hope we can try this out. Actually, 5.2, the solution is here already, okay? I believe 5.3 is not yet. It's similar, except for this guy, conjugate that y2. I think you have already learned how to find y2. hydraulic jam. So use that conjugate that equation. I hope you still remember y2 over y1 equals to, half minus 1 plus square root 1 plus 8 fr1 squared. Okay, use that formula and then you can find discharge. Alright, because I guess you need to know y2 as well, since you need y1, y0 and y2 to determine which equation that you want to use to find discharge. Alright, okay. So far, before we go into spillway structure, do you have any question? Ada soalan tak mengenai tak ada? Ya, saya.
Yang tadi doktor tanya tu kan?
Ya.
Dominan tak dominan tu apa maksud doktor? Bukan dia dah formula y0 tolak y1?
Tak, okay, macam ni. Okay, let's look at this, right? Why I said, right, if y1 is completely submerged, right, so you have to consider y0 because maksud saya di sini y1 dah tak mempengaruhi q dah. Nampak tak kalau lah dalam case, okay, kalau lah sebenarnya this hydraulic jam, right, is actually this hydraulic jam can actually shift up to the sluice gate. So y1 will be drowned. Y1 akan ditenggelamkan oleh y2. Boleh imagine tak senario tersebut? Kan? Jadi sebenarnya y1 dah tak memberi kesan pun kepada q yang akan keluar nanti. Boleh?
Boleh.
Alright, okay. So that's why kita kena semak dulu syarat dia. Y1 tolak Y1 kalau lebih besar daripada Y2 ataupun kurang daripada Y2 lah. Itu kesnya. Alright. Okay, now I hope you can try this. All these activities are straightforward. Okay. No question on sluice gate? If no question, go ahead with this spillway here. Now, alright, the term spillway, water spill out, right? So you provide a way. So it's a way where flow spill out. Alright, spillway is built in reservoir to allow flow of water to safely move downstream when reservoir is full. Now imagine this, if the depth of water behind the reservoir or the dam, right, is so high, right, above the crest, of course it will spill out, right? So this spillway provide, safety measure. It allows water to move downstream. Now, of course, the best design. In our course, we are not going to teach you the design of spillway. Actually, if you are interested, right, you can further your study into Masters of Hydraulic and it could be Hydraulics, Hydrology, and Water Resources Engineering, where you can actually learn how to design them, alright, or even spillway. Okay. Now, of course, the best design of spillway is smooth spillway. That means you allow the water to smoothly flow downstream. Okay. This is, these photos are taken at Sembrong Dam. Okay, this is a structure, right, of spillway. And then there's actually a gate as well. Gate below this structure. You can actually allow water to go out from the dam. You kind of control the level in the dam, the storage shaft. Right. This is at the toe, coming out from the spillway. You have at the toe here the steaming basin. This is what we are going to design. Alright. So you have examples of spillway here. You can go through this. This is on the design part. This is not in detail. This is just example. There are many more, examples of spillway. This is just one. I'm just showing you. Of course, H1 is the height of water above the crest. Alright. Now, the third structure here I guess I'm just going to go up to weir only for today class, because going too much, we couldn't, learn too much. We'll just go slow, right? Now, what is weir? Weir is overflow structure, alright? This is, of course, we are looking at the side view. Overflow structure built across an open channel to measure rate of flow. Alright, so when I said measure rate of flow, you know that our purpose would be to find Q. Okay, so we will offer simple and reliable method because we just built a structure across the open channel. Okay, this is called net. Right, water coming out, you have net there. Now, this is called net, and then you have crest here. This is known as sharp-crested weir because the width of the crest is not as wide, alright, as the net. Alright, you have this 60% factor. Alright, now the depth of water above the crest of the weir is H1. The height of the weir is P. Alright, the symbol used is P. Alright. Now, classification of weir can be made based on, whether you are looking at the type, alright, the opening, the width of the crest, or even whether it's submerged or not submerged, alright. Now, based on width of the crest, it can actually be classified as broad or sharp-crested. Of course, whether it's broad or sharp-crested, it depends on the width of the crest and you compare it with the net thickness. If the thickness of the crest is more than 60% of the net thickness, then it is broad-crested. It is classified as broad-crested. Now, based on opening of weir, alright, opening of weir, if you look at, it's not here, this opening. You can also classify the weir as triangular or V-notch, alright, rectangular. Later on I'll come back, what is the set, surprise and contractile rectangular, and also cephalitic, alright. This is a trapezoidal, but special trapezoidal when the side slope is 1 to 4. Okay, I'll come back to this line. Alright, let's go back. So now you have category. Depends on what kind of aspect you are categorizing the weir. Alright, it can have different weirs. Alright, you have plate weirs. This is broad crested. If you look at this, the crest is broad. And then you have sharp crested, and then the opening is V-notch, alright, or triangular. And then you have dam spillway with weir, alright. So all these are examples of weir, alright. Weir is this here, alright. Okay, now, just like I said, I'll come back to this, alright. What's the difference? You have B and C rectangular weir, surprise is, look at the side. You compare it with C. Here, it is still a rectangular weir, but the side here, alright, basically the opening of the weir is smaller than the width of the channel. In this case, alright, the opening of the weir is as wide as the width of the channel. So this is suppressed, right? The side is suppressed, right? Okay, to the side of the channel. Here, it is contracted, right? The opening is contracted. So you have L. Normally this L here, since it depends on how many contraction, it could contract only at one side. Here, two sides. Alright. Here, 0 side contraction. Here, 2, n equals to 2. And sometimes you will have only one side being contracted, so n equals to 1. You need to calculate the effective length. L subscript E is the effective length. That depends on the numbers of contraction. You have a factor of 0.1 n. Alright. We'll go to that later. and you have this width of channel B, and length of channel is actually measured bottom of the cipolity weir 1 to 4. Now let's look at rectangular weir here. Now rectangular weirs are divided into surprise. By now you should know that the weir opening is span full width, that means as large as the width of the channel. Contracted, that means the opening is smaller than the width. It could be contracted at one side or both sides. Alright. Now discharge. Just like we said, the function of weir is to actually measure rate of flow, right? So now we are going to find discharge. Discharge over sharp-crested, fully ventilated, free-flowing. Alright, this is a typical equation. It's given as 2/3 CD square root 2G LH to the power of 3/2. H1, you know already, is the depth of flow above the crest. L is the width of the channel, the weir opening, and then CD is the coefficient of discharge. Now, where does this formula comes from? Typically, whenever you see a rectangular weir, this is the formula. It comes from experimental. I believe you have gone through this Buckingham I theorem to create formula, right? That means you know that you have parameters of Q, C, L, and H. You actually try to arrange, right, to get this formula. Now, as I told you, CD could be given, or the question could give you CV and CC, alright? Coefficient of velocity and contraction. You could actually find CD, or alright, you actually, so far so good, I hope you actually can find CD. If the question asks you to use the Rybach formula, then you can use this formula. Depending on, first, which set of formula you want to use, you need to find the ratio of H1 over P. H1 is the depth of water above the weir, and then P is the height of the weir. So check, alright, which is related, and then you could actually use whichever, alright. Now, supposedly, right, then. Now, the discharge coefficient has smooth transition between the two equations. Actually, this is the one, alright, and this is one. Now activity 5.4. Alright, we'll just look at the first part of the question first, because we haven't looked at, how to the formula of triangular notch. We just look at the formula of rectangular weir only, right? Now you have sharp-crested weir installed in a rectangular channel, discharging flow under a head of 0.2 meter. And also this coefficient of discharge 0.6. Find Q if 1 meter width rectangular weir is used. Now do you still remember the equation? Q equals to 2/3 CD square root 2G L H1. This is which is given, right? The head of flow H1 0.2. L is the width of the weir, and then coefficient of discharge is given as well. So straightforward, you apply the formula, you have it. Here's the thing. Before we go into here, let's look at this for a while. The question actually have rectangular, triangular, trapezoidal. You'll come to a slide where, here, I'll show it first. Rectangular is 2/3. Triangular is 8/15. CD square root. Alright, we have tangent θ/2. And trapezoidal is this. Here's the thing. Actually, if you combine rectangular and triangular notch, okay, what I'm saying here, let's look at this, okay. Okay, let's look at this. If you combine, you have a rectangular notch, okay, and then you have a triangular notch over here. Actually, if I break this, okay, I put it here, it actually can become a trapezoidal notch, alright? So I can actually combine this formula, the triangular formula with the rectangular formula. I can actually get the trapezoidal. If you don't believe me, let's look at this. Alright, let's go back here. We have this formula 8 over 15, right? H to the power of 5 over 2, right? Don't worry about this, okay? Look at this. If I open up this is a trapezoidal equation. This will become 2 over 3 CD square root 2 GH L to the power 3 over 2. And there's another term, okay, which is 8 over 15, because this is a factor, right? 8 over 15. H to the power of 5 over 2, alright, square root of course, we have this, times tangent theta, alright. So this is the triangular formula just now. Actually, the trapezoidal formula is actually a combination of the triangular and rectangular formula, right? So this is, we'll come back to this formula. We'll just go through, right? Now, you know that rectangular, right, doesn't have vertex angle, or you don't have side slope, right, basically. So therefore, the equation, right, doesn't have this theta. Whereas for triangular notch, you have theta, as well as trapezoidal, you also have theta. So I think by now, when we give you this formula and we are asking you to solve a certain shape of weir, you should know which formula you want to use already. Alright, trapezoidal, this is the formula. Triangular is, 8 over 15 one, and then the rectangular doesn't have the theta one, right? The rectangular one, okay. So this is just to distinguish, right, the formula of weir, alright. Now, let's look at one example right here. This is a surprise rectangular weir. Surprise, that means the width of the weir is the same as the width of the channel, alright? It's not being contracted at any side, alright? At any side. So you have this weir 0.75 meter high. So can I have Mimi? Mimi, can you help me?
Yes, doctor.
Mimi, 0.75, what is the symbol used? What is it? Is it H1 or P or L?
0.75.
75, yes.
P.
P, thank you. How about 0.5 here? What is it?
H1.
Correct. And 1.5?
1.5 is L.
Alright, great. L and also is the same as B, right, in this case. Thank you.
Yes.
Alright, so you have that. Now I guess you know how to use the equation already. Okay, well, you have this. Okay, now does this say okay, CD is not given, so since H and P are provided, we can actually find for your CD lah in this case. Alright, you have that. So CD is such, so you can actually find for your discharge, you substitute LH, that's why I asked Mimi just now. Alright, so this is just application. Alright, you know what, I think this formula here, right, we have to check again, because normally CD would be less than 1 lah, typically. Alright, we are going to check again this schedule. I might have typo there, right? Okay, I'll let you know. Okay then, You have that already. Let's look at this. Contracted weir has length, okay, which is smaller. Why I say that? This is front view, okay? This is front view. Why I said we actually need to use LE instead of L. Just now, alright, since it is suppressed weir, we actually use our LE equals to L. In this case, when it is contracted, we need to use LE in our calculation, not L. Why? Okay, you know, let's look at this. This is front view of the weir. So you have two contraction, left and right. You have one contraction, and you have 0. This is suppressed. This is, if you look at here, 2 contraction, n equals to 2. This is one side contraction, that means equal to 1. Either one, left or right. Look, these 3 diagrams at the bottom here is when you are looking from the top. Alright, when you are looking from top of the weir, look at this. Since you have contraction, the flow actually is being diverted. It's actually, the flow area is reduced, which is smaller than L, so therefore you need to find the effective length, LE. It's not this, it's actually for, in this case, it's just go through smoothly, right? Because there's no contraction, right? But once you have contraction, right, the flow bend, okay, that would actually reduce the, that's why you have this vena contraction, vena contracta, right? Actually, the depth is actually smaller than the opening, basically, yeah? Now, how are we going to use this? Right, the same formula, it's actually the same formula, except I've introduced subscript E here. Now, what is LE? LE is L minus 0.1 n times HE. Now, if n is 0 equals to 0, what does it mean? That means it is suppressed weir. So LE becomes L. That means it's come back to L. But if n is either 1 or 2, that means your L is actually smaller lah. Alright? LE, what I mean is your LE is smaller than L lah. Okay. Because minus some correction factor, right? Okay. So what is n? Is number of n contraction. Okay. This is, okay. Now, there's another formula, Bayesian. So we learned about rapport, Bayesian, and then we have CC times CV to get CD, all those formula. Okay, so there's this another formula which is Bayesian, which is this. Of course, definitely will provide you this formula. I cannot remember too. Now, how does this formula come out? Right? It actually comes from experimental data. People do experiment and they come out with this formula. When you further your study, or you are doing, your career is in research, you can come out with more formula, and everyone can use the formula as well. Alright? Of course, you need to give the condition of your experiment. Right? Now, activity 5.6 is actually the involved calculation of discharge when both sides are contracted. That means n is equal to 2. So if it's n equals to 2, you need to find LE. Alright? Of course, there's this equation of, since I guess you can try to find CD using Weber. In this case, they use Bayesian formula. So you can try it out as well. So discharge is 0.9796. You know what? You have all this activity provided to you. Try it out on your own, alright? And then check your solution against the check your answer against the solution provided. Okay. Now I guess I'll go just not the activity. Okay. I guess there's only few slides. I'll just go through it lah, because just now actually I already talked about this triangular weir as well as trapezoidal. Look at this. This is triangular weir. Alright. Theta is theta over 2. Oh, sorry. The formula here is actually theta over 2. Right. Alright. Here's the thing. This is theta. Theta over 2 means half of this theta. But if you look at here, we are using, if you combine this, it's actually 2 theta. Half of this is actually theta. It's actually similar to, this case when you break it. Alright? Since just now in trapezoidal case, you have 2 theta. Half of it is theta. In this case, the vertex angle is theta. Half of it is theta too. That's why I said the formula is actually for trapezoidal, the formula is actually the combination of rectangular formula as well as the triangular formula. You get this trapezoidal formula. Now, except for when the slope is 1 to 4, it is known as cipolity here, which is this guy, cipolity. Alright, but there's no explanation on it. Don't worry then. Okay, try all this out. Okay, you have exercise, not much exercise. I think you have 1 more hour, right, for this hydraulic class. Try it out. It's very straightforward. We'll continue our class with design of energy dissipated structure next Thursday. You guys, do you have any questions so far?
No.
Doktor,
Yes.
untuk angle yang trapezoidal tu, theta dia memang kita guna 45.
Tak. Bergantung.
Okey. Kasih doktor.
Sama-sama. Ikut soalan lah. Is there any question? I don't give you question. Just a second. I think in your exercises you probably have question. I already give you assignment for chapter 5. I've already uploaded. You may try it out. Okay?
Okey doktor.
Alright. The rest of the slide will continue next Thursday lah. Is a bit too much lah for today. Yes, saya.
Yang coefficient of discharge.
Yeah. CD.
CD yang 0.596 to 0.607. Kiranya kalau tak bagi, ambil nilai tu.
Okay. Soalan mungkin akan bagi terus nilai CD. Mungkin dia akan bagi nilai CC dan CB. Maknanya kena darabkan lah untuk dapat CD. Boleh Mungkin disuruh guna formula Rehberg. Of course formula tu dia akan bagi. Mungkin, tapi actually dalam soalan dia akan sepatutnya dalam soalan dia akan nyatakan lah which formula you need to use, or there's another formula which is the Bayesian one. Just in case the question doesn't give you any formula to find CD, you just assume, you say using Bayesian, this is the CD, for example, if you want to use Bayesian formula. Boleh tak?
Boleh tak tu?
Okay.
Okay.
Alright. Ada any more question?
Doktor, saya nak tanya.
Yes, Haris.
Untuk final nanti soalan dia macam contoh ke dia akan lagi
Dia sebenarnya takkan lari. Sebenarnya macam contoh soalan, for example, test 2, right? You have question, right?
yeah.
If you look at it, it won't go far from your syllabus on your lecture notes. Am I right? Dia takkanlah bagi yang pelik-pelik sangat lah.
So kebanyakan soalan akan direct lah doktor kan?
I won't say exactly direct. Itu sangat mudah, betul tak? because we are actually trying to help you out to be an engineer later. Kita mungkin bagi soalan yang open-ended. That means we'll throw you some variables. Based on what you have learned, actually you should be able to do it lah. So jangan risau. Kita takkan bagi yang tricky sangat lah. Haris ya?
Faham doktor.
Thank
you.
You're welcome. Okay. Okay, kalau tak ada soalan, kita jumpa hari Khamis boleh. I'll see you on Thursday then. Alright?
Boleh doktor.
Alright, see you
Okay,
guys.
thank you doktor.
Yeah, okay.
Doktor.
Thank you.
Thank you doktor.
Thank you, doktor.
Thank you,
You're
doktor.
welcome.
Thank you, doctor.
You're welcome. You're welcome. You're welcome.
Thank you doktor.
You're welcome.
Okay doktor, thank you.
You're welcome.
Doktor,
Ini saya.
assignment 4 nak kena submit bila?
Saya rasa saya bagi tarikh Khamis
Sebelum-
ni kan?
Khamis
Khamis.
9.
Ya, betul.
Assignment 5 sekali ke ataupun
Tak. Kalau assignment 5 dah siap boleh hantar sekali. Tapi saya rasa kalau habis syllabus assignment 5, biasanya saya akan bagi 1 week extra.
okay. Okay, thank you doktor.
You're welcome.
Terima kasih.
Sama-sama. Now, do you have any question? Farahin? If you don't have any more question, I'll end this session. Take care.